The subject of this tutorial is resonance. Resonance is a phenomenon that arises in many physical systems. It comes about when there are two forms of energy storage in a system, and you have the transfer of energy back and forth from one form to another, creating an oscillation at some specific frequency. To illustrate resonance in electrical circuits, we'll begin with a simple parallel RLC circuit driven by a current source. And we're interested in the voltage across the capacitor, V, which describes energy storage in the capacitor, and the current through the inductor, I, which gives us 1/2 Li squared, gives us the energy stored in the inductor. The current source is an impulse, Q U0 of T. So parallel RLC driven by an impulse of current. And we're going to assume that this circuit is initially at rest. That is, for t less than 0, there's no energy stored in the capacitor, V is equal to 0, and there's no energy stored in the inductor, I is equal to 0. Now we need a differential equation to begin to arrive at solutions for voltage and current. There are just two nodes in this network, this connection between the four elements at the top, the connection between the four at the bottom. So I will write Kirchhoff's current law at this top node, setting the current produced by the source equal to the sum of the currents in the capacitor, the inductor, and the resistor. So that differential equation looks like Q U0 of T, the current flowing in from the source, equals C dV by dt, which is the current flowing in the capacitor, plus 1 over L integral of V dt, the current flowing in the inductor, plus G times V, where G, the conductance, is just the reciprocal of the resistance. It's convenient to use conductance instead of resistance because that gets me all the coefficients in the numerator. So the first question is what happens when the impulse comes along at t equals 0? There are two ways you can go at that. You can look at this equation and recognize that the impulse must be matched by the highest order term on the right, highest order in terms of differentiation. That's this term. So an impulse must produce an impulse in c dv dt, and that means that V must change in a stepwise fashion. To do it a little more formally, we can integrate both sides of this equation with respect to time through the origin. So on the left, we get the integral from 0 minus to 0 plus. I'll take the constant Q outside, U0 of T equals C integral 0 minus to 0 plus of dV plus 1 over L double integral of V, I'll call it V dx, dummy variable dt, both from 0 minus to 0 plus, plus G integral V dt. Well, with that equation, we can now interpret what's happening to the three terms on the right. This term, the first term, The term on the left is just q, because the integral of an impulse through the origin is the area under the impulse. That's just 1 by definition for the unit impulse. So q equals the integral of dv through the origin multiplied by c is the function v evaluated from 0 minus to 0 plus. This term, the double integral in v, must be 0, because v may change instantaneously at the time the impulse hits, but there's still no time to build up any area under it. And likewise, this integral must be 0. So what we learn from this is that q equals c times v of 0 plus minus v of 0 minus. This is 0. We said the thing was initially at rest. So v of 0 plus, the voltage across the capacitor after the impulse is passed, is just q over c, the charge in ampere seconds divided by the capacitance. And for convenience, we'll call this v sub 0. It is the voltage across the capacitor at t equals 0 plus. So we now know the initial voltage. We want to solve this differential equation to evaluate how v responds with respect to time. Now notice that once the impulse has passed, the left-hand side of the equation is 0. That is, the impulse has value only for t equals 0. So the left-hand side disappears, and we're left with the differential equation for the circuit, which has no driving function. That is, we're left with the homogeneous equation. In other words, the circuit, once the impulse has passed and charged up the capacitor, is unforced. So what we're going to see here is the natural behavior of an RLC circuit. Now let me differentiate this equation once with respect to time in order to get a pure differential equation. The left side disappears. For t greater than 0, the left side is 0. So for t greater than 0, the differentiating once, we get the differential equation 0 equals c d squared v dt squared plus 1 over L times v plus g dv dt as the homogeneous equation for the circuit with the source removed. Now what I want to do is divide all these terms through by c. So this becomes 1 over LC, and this becomes g over c. And then I'd like to introduce two coefficients, specifically 1 over LC. We will call omega naught, some frequency omega naught squared. Omega naught turns out to be the natural resonant frequency of the circuit with no damping. And we will call this coefficient g over c 2 times alpha. Alpha is the damping factor. So we've made two definitions. One of omega naught squared, one of alpha. And let's look now at the equation written in that form. If we repeat the circuit here with the source removed, since it produces no current once t equals 0 has passed, here's our circuit. RLC. This is the current we're looking for, and this is the voltage. And what we know is that d squared v dt squared, the differential equation which we derived in a previous sheet, d squared v dt squared plus 2 alpha dv dt plus omega naught squared v equals 0. Homogeneous equation. We also know that v of 0 plus is equal to this value we calculated by taking account of the impulse, V0, and I of 0 plus equals 0. That is, the double integral which produces the current in the inductor has no value for 0 plus. And we have made two definitions, one of omega naught squared equals 1 over LC, and 2 alpha equals G over C. Now, this is a linear differential equation, constant coefficients, second order, and we can proceed to solve it exactly as we did for first order equations. That is, assume a solution of the form V equals some constant times e to the st, where s is a constant. Substitute it in and find out what value s must have in order for that assumed solution to actually be a solution. So we assume that the voltage V of t is of the form a constant, e to the st, s is a constant, substituted in the differential equation. If we do that, remembering that each time we differentiate this thing, we get it back multiplied by s. So the first term becomes s squared a e to the st. The second term becomes 2 alpha a e to the st. And the third term is just omega naught squared a e to the st, all equal to 0. If I factor out the a e to the st, we get s squared. Sorry, I left an s out of here. When I differentiate this once, we bring out an s. S squared plus 2 alpha s plus omega naught squared equals 0. Now, the only way that equation can be equal to 0 is if the thing in the brackets, the characteristic equation of this unforced network, no source, the only way it can be 0 is if the thing in the brackets is 0. If a is 0, it's 0, all right, but that's not a very interesting solution. And e to the st cannot be 0 for any value of time. So we must set s squared plus 2 alpha s plus omega naught squared equal to 0 in order to get a solution. This is the characteristic equation for this network, the unforced natural characteristic equation of the circuit. And now we need to find the roots of this quadratic equation. Those roots are of the form S1, S2, there's two of them of course, S1, S2 equals minus alpha plus or minus j, square root of minus 1, times the square root of omega naught squared minus alpha squared. So we get a pair of roots which, if alpha is less than omega naught, are complex. If alpha is bigger than omega naught, then we get another square root of minus 1, canceling this one, and we have simply on the right side here alpha squared minus omega naught squared. So the roots can be either real or complex depending on the relative values of alpha and omega naught. There are in general three circumstances. I think we need a different pen here. There are three circumstances. There is one in which alpha is equal to omega naught. And if you look back at this equation, if alpha equals omega naught, the imaginary part of this root disappears, and we have S1 equals S2 equals minus alpha. S1 equals S2 equals minus alpha. So you have two equal negative real roots. Second possibility is that alpha is greater than omega naught, in which case this term, the second term, is no longer imaginary, it is real. And I get a factor here which is added or subtracted from alpha. So in this case, I get two negative real roots, not equal. And the final case, the one we're interested in here, the most interesting one, is when alpha is less than omega naught, in which case I get two complex roots. This is referred to as the underdamped case. When alpha is smaller than omega naught. When alpha is smaller than omega naught, as you can see from that equation on the previous sheet, you have a pair of complex roots. And you can get, in this case, oscillatory behavior. The other two cases are not terribly complicated, but not overly interesting either, and we're not going to talk very much about those. Let me do just make one more comment about the structure of these roots, which may be helpful as you keep the several situations in mind. If we draw a complex plane, that is, if we imagine this as the real axis and this as the imaginary axis, so I can plot every complex number is a plot in this plane. The complex roots for alpha less than omega naught reside at a negative value on the real axis of, that is, this intercept is minus alpha, and the intercepts on the imaginary axis are plus omega d and minus omega d, where omega d is just omega naught squared minus alpha squared. And this is referred to as the damped natural frequency. In contrast with omega naught, which is the undamped natural frequency. It is the natural frequency when alpha goes to 0. It turns out that this relationship has a locus for the roots in the complex plane, which is a circle, a half circle, centered on the origin, which looks like this. These are the two roots. The values of the roots when alpha equals 0, in other words, if I make alpha very small, these roots move a little bit higher, lower on the imaginary axis. Those asymptotes are omega naught and minus omega naught. And the radius of this circle is omega naught. So the undamped case, which we're interested in, has this pair of roots on this circular locus. If I make alpha bigger and bigger and bigger, these roots move down until they converge. And when the two converge at this point, that is the critically damped case. If I keep making alpha larger and larger, the roots move, one moves in and one moves out along this negative imaginary axis. But the case we care about here is the underdamped case with the pair of complex roots, leaving aside this first situation called critical damping and the second situation called overdamping. So we know now what the roots are. We can write the general expression for the voltage, V of t. There are two roots, and so V of t must have two terms. One must be the form A1 e to the minus S1t plus A2 e to the minus e to the plus e to the plus, both cases, plus S1t plus S2t, where S1 and S2 are these complex numbers. That is, S1, just to repeat it, to have it in mind here, S2 are minus alpha plus or minus the square root of omega naught squared minus alpha squared. If we substitute those in, we get an expression for V of t, which is the form A1 e to the minus alpha t e to the plus j omega t plus A2 e to the minus alpha t e to the minus j omega t. I arbitrarily put the plus j omega t here and the minus here. They could equally well go the other way. It's taken care of in the a's. The current in the inductor, I of t, is 1 over L, integral of V dt. I can integrate this readily, and I end up with an expression which has the same kernels. That is, the current expression will have some coefficient. I'll call it A1 prime, which will be a complex number now, because I bring out a 1 over j omega t, we do the integration. Some A1 prime times e to the minus alpha t, e to the plus j omega t, plus some A2 prime, different from A2, but proportional to it, times e to the minus alpha t, e to the minus j omega t. And so you can plug in, you can now plug in the initial values. V of 0 must be capital V sub 0, the value we found from the effect of the impulse. And I of 0 plus must be equal to 0. That gives you two algebraic relationships for the constants A1 and A2. Remembering that A1 prime and A2 prime are proportional to A1 and A2, just modified by the multiplication by a complex number, gives you two algebraic equations which you can solve for A1 and A2, put them back into the original equation, collect up the assorted terms, and you're all done. Instead of doing that, I will make an approximation which gives us a set of results that are approximately correct and which give us a little more insight into the way the circuit works. And the approximation we wish to make is that alpha is not just less than omega naught, but it is much less than omega naught. And this is a situation which is lightly damped. If you remember that alpha is equal to G over C, 2 alpha is equal to G over C. So the way to make it lightly damped is to make G smaller and smaller, which is equivalent to making R larger and larger. If you make the resistor large enough, it has very little effect on the currents flowing in the inductor and the capacitor. So we want to talk about the lightly damped case. If we do that, these exponentials combine nicely using the Euler equation to give you two functions, not of complex exponentials, but of sines and cosines. And specifically, V of t turns out to be V0 e to the minus alpha t cosine omega naught t. And I of t is equal to V0 square root of C over L e to the minus alpha t sine omega naught t. And as I say, these are approximations. The exact solutions have some function multiplying V0 in both cases, and instead of having omega naught here at the undamped natural frequency, they have omega d, the damped natural frequency. But if alpha is much, much less than omega naught, if alpha squared is much, much less than omega naught squared, and omega naught squared, sorry, this should be square, omega naught squared is just approximately equal to omega naught. That is the situation when the roots are very close to the axis. So it is that lightly damped case that we now want to investigate. Notice that the exponential e to the minus alpha t, which affects both the current and the voltage, provides an envelope, if you will, which gradually attenuates the cosine of the sine function as time goes on. E to the minus alpha t, you're familiar with that. It's a decaying exponential. So it starts out at value 1 for t equal to 0, and the initial voltage is just V0, which is correct. The initial current is 0 because the sine is 0 at t equals 0. But as time goes on, this cuts down both the sine and the cosine. So the function plus or minus V0 e to the minus alpha t creates, in effect, an envelope on the cosine and sine. Now I want to sketch one of these. I wouldn't dare attempt to sketch both and keep them in phase, in proper phase relationship, but let's sketch just the voltage. This is omega naught t. This is the voltage V of t. And if I sketch here V0, and down here an equal distance down minus V0, this is the origin. These, the exponentials, which decay towards 0, provide an envelope into which the cosine function must fit. This is a plus or minus V e to the minus alpha t, so it's supposed to be symmetrical. And if I let this be 2 pi, and this be 4 pi, 6 pi, and so on, 6 pi, 8 pi, then the function starts out as a cosine, goes through one full cycle in 2 pi, so it comes down, comes back up, and is back up to not the original value, but the original value attenuated somewhat, 2 pi. Does the same thing in the second period. Comes back to a smaller value. Likewise in the third period, and so on down. So the response is a cosine attenuated by this function e to the minus alpha t. And the current, were I to draw it, would have exactly the same form, only it would start out not at a value, a finite value, would start out at 0 and be 90 degrees out of phase with this cosine function. Now let's look for a minute at stored energies. The energy storage in the capacitor, the instantaneous energy storage in the capacitor, is 1/2 C V squared. And the instantaneous energy storage in the inductor is 1/2 L I squared. So if I take the value we have for V and substitute it in here, I get 1/2 V0 squared e to the minus 2 alpha t, when I square that term, times cosine squared omega naught t. And for the inductor, I get 1/2 L I squared. If we look back at I, when we square it, we get V0 squared times C over L. The radical squared is just C over L. So it's 1/2 L V0 squared C over L e to the minus 2 alpha t sine squared omega naught t. And if I cancel the L's here, this is just 1/2, I left the C out up here, 1/2 CV squared. I got the V squared all right in the 1/2, but I didn't put the C in. It belongs there. Down here I'm left with the C, so I have a C in the numerator times V0 squared e to the minus 2 alpha t sine squared omega naught t. And you see that these coefficients are equal. The energy stored in the inductor varies as sine squared, but has a peak value for any particular time, any particular e to the minus 2 alpha t, has a peak value which is equal to the peak value of the energy stored in the capacitor at a different time. That is, the energy stored in the inductor is at a maximum when sine equals 1, a quarter cycle after the energy stored in the capacitor, which is a maximum when cosine equals 1. The point is, however, that the total energy stored in these two energy storage elements, capacitor and inductor, is just adding these two together, 1/2 C V naught squared e to the minus 2 alpha t times cosine squared plus sine squared, which equals 1. So the total energy stored at any instant of time, shared between the inductor and the capacitor, at any fixed time, is a constant. As time goes on, the energy decays exponentially with a time constant 1/2 alpha, decays exponentially towards 0. But at any instant of time, the total stored energy is constant. When cosine is 1, all the energy is stored in the capacitor. When sine is 1, all the energy is stored in the inductor. This situation, which in the RLC circuit amounts to energy flopping back and forth between the inductor and the capacitor. When cosine is equal to 1, that is when omega t is equal to 0 or 2 pi or 4 pi, n times 2 pi. When the cosine is equal to 1, all the energy is stored in the capacitor. A quarter cycle later, when sine is equal to 1, all the energy is stored in the inductor. And it flops back and forth, first in the electrostatic form and then in the magnetic form, magnetic stored energy forms, flops back and forth, in each cycle giving up a little bit for power dissipation in the resistor. The resistor dissipates power at a rate, at a value V squared over R. So the resistor, whenever there's voltage across it, is changing electrical energy to heat, and that goes on all the time, gradually using up the stored energy that was in the system at the start. Notice that 1/2 CV0 squared is the energy that we put in the capacitor with the impulse. That is, the initial voltage is V0. 1/2 CV0 is the initial voltage and the initial energy, which got there entirely as a consequence of the impulse. Let's look now at the energy loss. The rate at which energy is being lost in the resistor is the interval over some period of time of the power lost in a resistor. Well, the power loss is G V squared equal V squared over R, if that makes you more comfortable. GV squared I will write as G over 2 times V0 squared e to the minus alpha t cosine omega naught t, using the value, this is e to the minus 2 alpha t, and this is cosine squared. Using the value for v that we found previously, v was v0 e to the minus alpha t cosine omega naught t. We square that, it looks like this. The energy loss in the resistor averaged over some period of time is just the integral over that period of time of p dt. And let me take it over a period. That is from t, any time t, up to t plus capital T, where capital T is the period, and it's just 2 pi over omega naught. So t is the period of this oscillatory function. If I do this and make the assumption that alpha t does not change a lot during one period, that's equivalent to the assumption of very little damping, light damping, I can take out the e to the minus 2 alpha t because it's not changing much during one period over which I'm integrating. That is, we're assuming that alpha is much, much less than omega naught. So this term is approximately constant through one period of the cosine. So we get out front g v0 squared over 2 e to the minus 2 alpha t. This wasn't very clear up here. It's 2 alpha t. E to the minus 2 alpha t times the integral of cosine squared omega naught t from t up to t plus capital T over a period. This is readily integrable. You can recognize that cosine squared is equal to 1 plus cosine 2 omega naught t, and integrate it in that manner, or look it up. But in any case, it comes out to be a value which over one period is just 2 pi over omega naught. So that's the energy lost in one period. Let's now look at the energy lost per radian. This is the energy lost in a period. The energy lost per radian is just this value divided by 2 pi. So it's g v naught squared over 2 omega naught e to the minus 2 alpha t. And finally, I want to form a ratio, which is the energy stored at any time, the energy stored divided by the energy loss per radian. The energy stored is 1/2 CV0 squared e to the minus 2 alpha t. So we have 1/2 CV0 squared e to the minus 2 alpha t. And the energy lost per radian is g v0 squared over 2 omega naught e to the minus 2 alpha t. Well, most everything in here cancels. The 2's, the 1/2's cancel, the v0 squareds cancel. I'm left with omega naught, comes up in the numerator, omega naught c over g. Omega naught c over g. But we defined 2 alpha as g over c. So this ratio is just omega naught divided by 2 alpha, dependent just on the undamped natural frequency and the damping factor. That is a number that keeps appearing when you look at underdamped circuits, and it's given a name, which is Q, the quality factor. Omega naught over 2 alpha for the parallel resonant circuit. And so far, what we understand about Q is that it has the interpretation of the energy stored at any instant in the inductor and the capacitor, divided by the energy that's lost in 1 radian, not 1 period, but 1 radian. It's possible to give a slightly different and useful interpretation to Q as well. If you look back at the voltage, V of t, V0 e to the minus alpha t cosine omega naught t, and focus on the alpha e to the minus alpha t term for a moment, let's ask how much the e to the minus alpha t changes in Q cycles. In Q cycles. In other words, we want omega naught t after Q cycles will have the value 2 pi times Q. So if I take this t at that time, t is 2 pi Q over omega naught. And if I put it in here, this becomes minus alpha over omega naught, 2 pi times Q. Now remember, Q we defined as the value of the resonant, the frequency, divided by 2 alpha. So 2 alpha over omega naught is 1 over Q. The Q cancels, and all I'm left with is e to the minus pi. E to the minus pi is approximately 1 over 23. So by that 1 over 23, or about 4% of its initial value, in Q cycles, the exponential gets down to 4% of its initial value. And you can say, for all practical purposes, that the voltage is gone. This gives a useful interpretation to Q. That is, the number of cycles that must go by in order for the voltage to essentially disappear is Q. Now, before we go on and talk about a little more about aspects of the parallel RLC, let me simply note that all of this analysis, all of the analysis we've done so far, is applicable to some physical systems that you are familiar with. If you take, for example, a simple pendulum, a pendulum in a clock, you have a pivot with an arm and a weight at the bottom. This is a pivot point up here. And you can displace this pendulum off to the side, raising the ball slightly, and the pendulum will swing back and forth in an arc with a motion which, if the arc is not too big, if this angle theta is not too big, specifically if theta is small enough so that it approximates sine theta, this motion, the angular motion about the pivot, will be sinusoidal. What you have in this simple physical system is an interchange of kinetic energy with potential energy. When a ball is at this point or at this point, it's standing still for an instant before it reverses its motion and comes back. And at that instant, all the stored energy in the system is gravitational, potential energy. As the ball goes through its lowest point, it's moving at its greatest velocity. All the energy in the system is stored in the energy of motion, in kinetic energy. So there's a interchange back and forth of kinetic energy to gravitational potential energy as the pendulum swings. And if this is a lightly damped pendulum, if there's not much friction in that pivot, and if there's not much air friction, this motion will carry on for a while. It's gradually attenuated because there's always going to be some loss in here, unless you do this with a very good bearing and do it in a vacuum. But there's some loss of energy due to the motion of the pendulum through the air, and eventually it decays. In Q cycles, more or less it's gone. So the concept of Q, the concept of damping factor, the concept of resonant frequency, undamped natural frequency, all arise in the pendulum. They arise again in a somewhat more complicated way in a bell, with a bell. If you think about a good bell, when it's made of a high-quality bronze, it doesn't have too many loss mechanisms in it, and you whack that bell, give it a smart whack with a mallet, it will ring for some time. What you have there is the interchange of kinetic energy of the motion of the bell structure being swapped off with potential energy stored in the stressed material of the bell. Now, it's not a simple sinusoid. It's a much more complicated motion in that much more complicated structure. But you get a ringing sound, a damped oscillation, which gradually fades away as the loss mechanisms in the metal and in the air trickle away the energy that you put into it when you hit it with the mallet. So these concepts that arise in an RLC circuit that deal with resonance, all the things we've talked about here, arise as well in other physical systems, some of which you're probably familiar with. I would like now to go on and talk about resonance from the point of view of impedance, the impedance of this circuit, the RLC circuit. So we'll look at the impedance seen at the terminals of this parallel RLC circuit. And if we call this voltage V sub I bar, it's a complex number, complex amplitude, and this current I sub I bar, complex amplitude, the impedance, looking in at these terminals, Z. The impedance Z, as a matter of definition, is V sub I divided by I sub I. And now we can form this just by adding the admittances of these three elements. They're all in parallel, so the admittances add, and then taking the reciprocal of that, just as if these were three resistors and we were doing this with an all-resistive circuit. So the admittance of the resistor is G. The admittance of the inductor is 1 over Ls, and the admittance of the capacitor is Cs. If we clear of fractions, the impedance Z is Ls divided by GLS plus 1 plus LC S squared. And then if I divide through by LC, this becomes just S over C. The last term here I'll write as the first one here, S squared. This term becomes, the L's cancel, and G over C, which was 2 alpha, previous definition, 2 alpha S. And this term, 1 over LC, is just omega naught squared. So here's the impedance as a function of S. Same definitions as before, 2 alpha equals G over C. and omega naught squared equals 1 over LC. Now let's let S equal j omega and ask what the frequency behavior of this impedance is. If I substitute for j omega in this equation, we get z of j omega equals j omega over c divided by, well, there's an omega naught squared for the real part. And if I multiply j omega times itself, I get minus j omega squared, minus omega squared, minus, not omega naught, just omega squared. And then the imaginary part of the denominator is plus 2 alpha, plus j 2 alpha omega. This is omega squared, not omega naught squared. There are three ranges of frequency, or three frequency ranges in which we would like to look at this. Let's look at z of j omega when omega is much, much less than omega naught. If omega is much, much less than omega naught, this term is, the omega squared term is negligible compared to the omega naught squared term. So we have in this case, I can neglect this term. If omega is much, much less than omega naught, I can neglect the imaginary term compared with the real term, and we have just j omega divided by c in the numerator divided by omega naught squared in the denominator, and that's equal to j omega 1 over c omega naught squared. 1 over omega naught squared is LC. So the C is it cancels out, and this just equals j omega L. So at low frequencies, omega much, much less than omega naught, the impedance looks like an inductor, j omega L. Does that make sense? Well, the impedance of the capacitor varies like 1 over omega. So as we go to lower and lower frequencies, this gets bigger and bigger. The impedance of the resistor is fixed at R. The impedance of the inductor varies as omega. So I go to lower and lower frequencies, omega L gets smaller and smaller, and the L, the inductor, dominates the impedance at low frequencies. It's like having two large resistors in parallel with a very small one. The only one that matters is the small one, so it looks like an inductor. If we go to high frequencies, z of j omega for omega much, much greater than omega naught, what happens now is the omega naught squared is negligible. The omega is less than omega squared. We're dealing here with small values of alpha, so I will ignore the imaginary term in the denominator compared with the term omega squared, and then we get j omega over c divided by minus omega squared. These are both approximations. So this leaves me with j upstairs and a minus sign downstairs, translates to a j downstairs. The omega here cancels 1 down here, the c comes down, so this is equal to 1 over j omega c, which is just the impedance of the capacitor. Does that make sense? Well, yes. As omega goes up, this impedance gets larger and larger. It's proportional to omega. This one gets smaller and smaller. It's proportional to 1 over omega. So at very high frequencies, the circuit looks just like a capacitor. What happens at omega naught? Z of omega naught. These terms cancel exactly at omega naught. So the real term disappears. The j's cancel. the omegas cancel, and I'm left with just 1 over c upstairs and downstairs 2 alpha. 2 alpha is g over c. So z of omega naught, the c's cancel, is just 1 over g or r. So at resonance, at the resonant frequency omega naught, the parallel RLC circuit looks like a pure resistance. What is happening is that the admittance of the capacitor, which varies like 1 over j omega c, exactly cancels the admittance of the inductor, which varies like j omega c. And if you set up that equation, evaluating the magnitudes of those admittances, you find that at frequency omega naught, the two admittances exactly cancel. This does not mean that there is no current flow in the inductor and the capacitor. In order to illustrate that point, let's look at the circuit and compare the magnitudes of the current in the resistor with the current in the inductor or in the capacitor, G, L, and C. In other words, let's imagine that there is a voltage V sub I bar, complex amplitude V sub I bar across this network. The current in the resistor, which I'll call I sub R bar, and I want to compare that with the current in the capacitor, I sub C bar. The current in the resistor, I sub R bar, is just the voltage across this parallel combination, V sub I bar times G. The current in the capacitor is equal to the complex amplitude of the voltage multiplied by the admittance of the capacitor, which is J omega C. So the magnitude of the resistive current, the magnitude of the resistive current is just V sub I magnitude times G, and the magnitude of the current in the capacitor is just magnitude of V sub I times magnitude of J omega C, which is omega, in this case omega naught, times C, because we're driving this at resonance at omega equals omega naught. So if we take that ratio, the ratio of the magnitude of the current in the capacitor to the magnitude of the current in the resistor, we get capacitor, the V sub I magnitudes cancel, of course. We get omega naught C divided by G. Omega naught C divided by G. This is just omega naught over 2 alpha. And here's our definition for 2 alpha is G over C. So 1 over 2 alpha C over G, and this is, as a matter of definition, Q, the quality factor. So what this says is that if there's some current flowing in the resistor, say, to be simple, an ampere, and if the Q of this circuit, omega naught over 2 alpha, is 40, there's 40 amperes flowing in the capacitor, and exactly the opposite 40 amperes flowing in the inductor. That is, if this is I sub L, complex amplitude, flowing in the inductor, if you follow through the complex arithmetic, you will find that I sub C, complex number, is exactly equal to minus I sub L complex number. That is, these currents cancel, and there is a circulating current that flows in this LC pair, which is Q times as big as the current flowing in the resistor. So while the circuit at resonance looks like a pure resistance, you shouldn't ignore the fact that there's a whopping big circulating current flowing in the parallel LC combination. Now, almost done with the algebra here, but what I'd like to do now is approximate the impedance near resonance. The impedance as a function of omega we derived previously. I'll just repeat it here. It is J omega over C divided by omega naught squared minus omega squared for the real part plus J 2 alpha omega. And I want to approximate this for omega near omega naught. So I'm going to let omega equal omega naught minus delta omega, where delta omega is the deviation from omega naught. And then if I recognize that omega naught squared minus omega squared can be written as omega naught plus omega times omega naught minus omega. And if delta omega is much, much less than omega naught, that is, if we're looking for small deviations from resonance, this term is approximately 2 omega naught, and this term is just by definition delta omega. So Z of omega for omega near omega naught can be approximated, this is an approximation, by J omega naught over C divided by 2 omega naught delta omega plus J 2 alpha omega naught. That is, I'm ignoring omega naught. I'm ignoring delta omega when it appears added to or subtracted from omega naught, and accounting for it only in this term. We can form the magnitude of Z by looking separately at the numerator and denominator and forming the magnitude of each. So Z of omega magnitude is the magnitude of the numerator, which is omega naught over C, divided by the magnitude of the denominator, which is the square root of the sum of the squares of the real and imaginary parts. So we have 2 omega naught delta omega squared plus 2 alpha omega naught quantity squared, square root of. Now, if you imagine that the network, as we had in the previous sheet, the network has a voltage across its terminals, the power being dissipated in the inductance, I'm sorry, in the resistance, none is ever dissipated in the inductance. The power being dissipated in the resistor is V squared times G. So power dissipated in the resistor is V sub I magnitude squared divided by R, or V sub I magnitude squared times G. If the network is driven with a current, if it's driven with a current, as we depart from resonance, that is, as delta omega becomes other than 0, recognize that when delta omega is 0, the denominator just becomes 2 alpha omega naught. The omega naughts cancel, and we have the C cancels, and we end up with simply G as the value of this, R as the value of this at resonance, as we saw a page or two back. At resonance, the omegas cancel. I get 1 over C upstairs, 2 alpha downstairs, equals 1 over G or R. So if we're driving it with a current at resonance, the impedance is its largest value ever. It's the value R, and the power dissipated in R is its greatest. And what I'd like to form here is a value of delta omega at which the magnitude of Z is reduced to this value. Let me call this Z max when delta omega equals 0. So Z max is equal to G. And I want to find the frequency at which Z magnitude is equal to G divided by the square root of 2. Because if the magnitude of the impedance is reduced by the square root of 2, and if we're driving it with a fixed current, then the voltage across the resistor will be reduced by the square root of 2, and the power dissipated in the resistor will be reduced by half. It's 1 over square root of 2 squared. Well, this will be reduced by the square root of 2 when the real part equals the imaginary part. Remember, we got this value, Z max, by letting delta omega go to 0. The denominators became 2 alpha omega naught. If I make the real part equal the imaginary part, the denominator reduces to the square root of 2 times 2 alpha omega naught. And for that to occur, that is for the half power frequencies, the frequencies at which the voltage for a constant current drive is reduced by 1 over the root of 2, or the power dissipated in the resistor is reduced by a factor of 2. For the half power frequencies, we have to have 2 omega naught delta omega, the magnitude of the real term equal to the magnitude of the imaginary term, 2 alpha omega naught. The omega naughts cancel. So canceling the omega naughts, we end up with 2 delta omega equals 2 alpha. Now keep in mind what we're doing here. We're plotting the magnitude of the impedance, calculating the magnitude of the impedance near the resonant frequency, omega naught, versus frequency. At omega naught, the impedance is just equal to R, and it falls off on both sides. If this is on linear coordinates, it falls off in a form that looks something like this. When we get down, this is the value R. When we get down to a value at which the impedance is R over the square root of 2, the power dissipated in R is reduced by half. And this distance and this distance, the distances out to these half power points from the center, is delta omega. It's delta omega, and this is delta omega here. So the bandwidth of this resonant peak at the half power points is 2 delta omega. So the bandwidth at the half power points. Is equal to 2 alpha. The ratio of the resonant frequency, omega naught, divided by the bandwidth. The ratio of the resonant frequency by the bandwidth is omega naught over 2 alpha, which from our previous definition, long way back now, is just Q, the quality factor. So here's another third useful interpretation for the quality factor. If you have a resonant circuit, an RLC circuit, where the circuit is underdamped, the resistor is quite large, the conductance is small, alpha is less than omega naught, that circuit exhibits oscillatory behavior in the time domain. In the frequency domain, where you're driving the thing with a complex exponential at some frequency omega, it exhibits a resonant peak at omega naught, if alpha is small enough. Actually omega d, but if alpha is small enough, the two are equivalent. It exhibits a resonant peak in the frequency domain. And if you look at the bandwidth of that resonant peak, down to the point where defined by the point at which the power dissipated in a resistor is reduced by a factor of 2, half power, that bandwidth is just the resonant frequency, omega naught, divided by Q. So Q has a useful interpretation here. It is a measure of the sharpness of the resonant peak. The larger Q is, the smaller the bandwidth is, the sharper the resonant peak is. So we've seen Q. It arose first in the time behavior of this circuit, where we noticed that Q is defined as a measure of the energy loss, a reciprocal of the energy loss per radian divided by the total stored energy. To put that in non-reciprocal terms, the total stored energy at any point in time divided by the energy loss per radian is Q, omega naught over 2 alpha. It also has the interpretation that the oscillatory function that results when you put some energy in and let the circuit exhibit its natural response, the oscillatory response disappears in about Q cycles. And the final interpretation here is that the resonant frequency, omega naught, divided by the bandwidth, 2 delta omega, is just Q. So it's a measure of the sharpness of the resonant peak. All these interpretations coming back again to the same thing. Well, that concludes the discussion of parallel resonant circuits. Let me say just a couple of sentences about a series resonant circuit. I'm not going to pursue any of the analysis. You'll find it in the text, and it follows rather simply from what we've done here with parallel resonance. But if we take a circuit which is a series RLC, and we drive it with an impulse, in this case it's an impulse of voltage, lambda U naught of T. That dumps some energy into the inductor, and the circuit starts out with a circulating current. Notice that after the impulse is gone, this source can be replaced by a short circuit. It has a value only at t equals 0. That dumps some energy into the inductor. So the circuit starts out with a specific circulating current in this loop with no voltage across the capacitor. You find a current which varies as the initial current times cosine omega t, and a voltage across the capacitor which varies like sine omega t, omega naught t, if it's lightly damped. The only point I want to make is that while omega naught in the series resonant circuit, omega naught squared, is still 1 over LC, the damping factor, 2 alpha, which was C over G in the parallel resonant circuit, is now R over L. This is the damping factor in parallel resonance, which ought to suit your understanding of relative values. If I make R very small, that's making alpha very small, it's making the circuit lightly damped. As R goes to 0, this is just a series LC, which will go on oscillating indefinitely. But the loss mechanism, which is a series resistance in this case, steals a little of that energy being swapped back and forth between the L and the C on each cycle, and eventually decays to 0. All the detailed analysis follows very closely from what we've done. The only point I wanted to make in putting it on here at all was to emphasize that the damping factor in a series resonance circuit has a different definition. It's R over L instead of C over G, as it was for parallel resonance. Thank you for your attention.